Geometry is not done to be learned, it is made to be used. Simon Papet. Nothing is easier to learn than geometry, however useless it may be. Sasha Yetrin. Geometry is the act of correct reasoning from incorrectly drawn figures. Henry Poincaré. Hello to you and welcome to this third training unit entitled Geometry of the fourth module, Mathematical Thinking and Problem Solving. Like with the previous training units, which dealt with permutations and combinations, this training unit is not intended to give you content of mathematics. Geometry is one of the topics chosen as case study to demonstrate how you as a teacher can ask questions and direct students to think mathematically to solve a given problem. Geometry is one of the main branches of mathematics that is not well taught at the secondary school level. Quite often, mathematics teachers postpone geometry lessons until the end of the school year, and in so doing, they end up not teaching everything that was expected, or they do so in a hurry, which necessarily have a huge cost on students' acquired knowledge and skills. The reason why we want to impact you, firstly, by drawing your attention to this fact. Secondly, relegating geometry to the end of the school year does not always allow mathematics teachers like you to develop skills in teaching this branch of mathematics. Indeed, if knowledge awakens your abilities, it is experience that enriches your skills. But how do you enrich these skills without practice? Moreover, the part reserved for geometry in the mathematics program of our secondary education in Cameroon reveals that most of this geometry involves representations and transformations of shapes within the environment. These therefore require actions such as the perception of the physical environment, the production of forms and the transformation of the physical environment, and the determination of measures such as lengths, areas, and volumes, as well as the establishment of relationships between these different forms. Very often, mathematics lessons simply boil down to formulas and/or properties that students have to memorize without going through any mathematical reasoning beforehand, and you are now aware of the impact of this type of strategy on learners' results. On the one hand, and the enthusiasm for doing mathematics on the other hand. As we have emphasized in the first two training units of this module, using mathematical reasoning to solve problems is one of the most fundamental goals of teaching mathematics. This is why, in this training unit, through the activity that will be offered to you, you will see a concrete example of mathematical reasoning applied to geometry. This is just one of many strategies, and you can use others, provided to you will indirectly instill the skills of mathematical thinking in your students during your lesson. What is geometry? We can say that in the beginning, geometry was the science that measured the earth. Today, geometry is considered the branch of mathematics that is interested in the study of the properties and measurements of figures in space or on a plane. In its development, geometry employs concepts such as points, straight lines, planes, and curves, among others. History of geometry. The origins of geometry 2000 years BC are attributed to the repeated flooding of the Nile in Egypt. The first Egyptian land surveyors to regularly retrace the boundaries of agricultural properties in order to redistribute land fairly. The famous Greek historian Herodotus would say geometry is a gift from the Nile. At that time, they could calculate the area of quadrilaterals such as trapezium rectangles or isosceles triangles, although the calculation formulas only led to approximate values. The Rhind papyrus recopied 2000 years BC by the scribe Hermes gives this different information. After the time of Black Egypt, the Greek schools, through scholars like Thales, Pythagoras, Euclid of Alexandria, Archimedes of Syracuse, made geometry deductive. Gone are the days the formulas led to exact values. The properties are no longer allowed on examples, but are demonstrated in the general case. After the Greek era, it was not until the 13th century to see advances being made in the East and the Middle East among the Arabs and Indians. We note the development of new methods of calculating areas and volumes and the considerable advance in trigonometry. We have to wait for the European Renaissance to note the following notable advances. Birth of projective geometry leading to perspective representation in the 14th century. Birth of analytical geometry exposed by the mathematician René Descartes in his work Geometry by inventing the concept of coordinate systems. He then goes through algebra to simplify methods and demonstrations in geometry. In the 19th century, geometry experienced a new turning point with the birth of non-Euclidean geometries. Why should geometry be taught in secondary school? We will never stop saying it. It is imperative during your mathematics lessons that you refer to some applications of concepts being taught in order to capture and sustain the interest of your students. This is why, as the word leads, an example teaches, said by Joseph Joubert, we want to give you some uses of geometry in our society today. Geometry is used in many fields today, including architecture, imaging, infographics, robotics, mechanical engineering, and some scientific disciplines such as town planning, topography, astronomy, tomography, operational research, navigation, crystallography, etc., etc. As you have guessed, geometry forms the basis of so many fields and professions. This is why, as a mathematics teacher, it is necessary to make a commitment to teach it well to your students. The future of the whole nation strongly depends on it. Mathematical thinking and problem solving apply to geometry. Here we show an example of an activity that identifies the mathematical thinking that occurs in your student. Each step of the activity is a specific instruction that will lead learners to answer the question, what is the sum of the internal angles of any triangle? At the end, each learner should be able to establish that the sum of the internal angles of a triangle is 180 degrees. The prerequisite knowledge for this activity is the notion of any triangle and particular triangle and the ability to draw one. Students working together in small groups is the most recommended method, although it can be done individually. Problem situation. The purpose of the problem situation is to create that challenge that your students will want to take on. The situation may not be something they will come across in their daily activities, but it is something that is interesting enough to captivate the students and give them something they want to solve. Problem situation is as follows. As part of the activities of the school maths club, you have been asked to make a triangular sign, wooden sign, to present the activities of the club. The club president sketched this sign on a piece of paper and gave it to you. Unfortunately, you were surprised by the rain, and the sign drawing that was in your uniform pocket deteriorated as shown in the figure opposite. What was the measure of the angle? Let us follow the steps below as if we are doing the activity ourselves. Step 1. In your exercise book, draw 3 different triangles. Label them triangle 1, triangle 2, and triangle 3. Make sure your triangles are different types of triangles. Say equilateral triangle, isosceles triangle, scalar triangle, or right triangle. Here, each student draws different triangles. This step will allow your students to leave room for the variety of triangles that will justify the conclusion at the end. Step 2. Label the interior angles of each triangle using either letter A, B, and C, or X, Y, and Z. How many internal angles are there in each triangle? This step allows learner to count to get the number of angles, and notice that a triangle always has 3 internal angles. Step 3. Make a table to capture the sizes of the angles for each triangle. On the table, the first column will have the triangle, the second column and the value of angle A, the third column, the value of angle B, the fourth column, the value of angle C, and the last column, the sum of the angles. Measure the size of each internal angle and note in the table for each triangle. This step provides quantitative information by measuring the angles of each triangle. Step 4. Find the sum of these angles for each triangle. What sum do you have for triangle 1? What sum do you have for triangle 2? And what sum do you have for triangle 3? This step allows learners to quantify the sum to eventually establish a relationship. It also makes it possible to compare the different quantities obtained. Step 5. What do you see about the different sums? This step allows learners to observe individually or in groups that the sum of internal angles for all triangles is 180 degrees. Step 6. Ask 2 of your neighbor group their results. This step allows learners to compare and confirm their result and to realize that the sum of the angles is the same. Step 7. What can you conclude about the sum of the internal angles of a triangle? This step allows learners to generalize for any triangle and to deduce the general formula. As you may have noticed, learners through the instructions and questions in this activity are able to give a pictorial representation of a triangle by thinking and reasoning mathematically. They will derive a formula on their own, and it is not you, the teacher, who fits them with the formula. After the activity, points to remember. After the activity, you and your students can make the following written record, which can be taken as a course note in your learners' notebooks. Property 1. The sum of the measures of the three internal angles of a triangle is equal to 180 degrees. Whatever the triangle ABC, we have sum of angle at A plus angle at B plus angle at C is equal to 180 degrees. Special case 1. Right triangle. If ABC is a right triangle with the right angle at point A, we have 90 degrees plus ABC plus angle BCA is equal to 180 degrees. Then angle ABC plus angle BCA is equal to 180 degrees minus 90 degrees, which is equal to 90 degrees. Property 2. In a right triangle, the sum of the two acute angles is equal to 90 degrees. Property 3. If in a triangle, the sum of the two internal angles is equal to 90 degrees, then this triangle is a right triangle. Special case 2. Equilateral triangle. If ABC is an equilateral triangle, its three internal angles have the same measurements. This measurement is therefore equal to 180 degrees divided by 3, which is equal to 60 degrees. Property 4. In an equilateral triangle, each of the internal angles is 60 degrees. Property 5. If a triangle has two angles of 60 degrees, then this triangle is equilateral. Property 6. If an isosceles triangle has an internal angle of 60 degrees, then this triangle is equilateral. Conclusion. During this module, we will never stop reminding you that as a mathematics teacher, applying mathematical reasoning and problem solving in your activities during your lessons is essential and even a requirement. Through this training unit, we presented an example of an activity applied to a notion of geometry. As we have already pointed out, the activity we have proposed is not universal. That is why you must adapt it to your students and your context. For example, if your school has a multimedia center, You can perform the same activities by including ICT tools such as GeoGebra. As you know, coming together is a beginning. Staying together is progress. Working together is success. Don't forget to share your ideas and questions in the forum. You can also go to the TTP Community of Practice platform via the following link in order to discuss with the members of your clusters. Alone, we go faster, and together, we always go further. See you soon in the next training unit.